Welcome to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. In the last lesson, we discussed asymmetric and symmetric multiprocessing. In this lesson, we are going to start to explore more multi-core processors and multi-threading multi-core processing. So let's get started. Traditionally, symmetric multiprocessing systems have allowed several processes to run in parallel by providing multiple physical processors. However, most contemporary computer hardware now places multiple computing cores on the same physical chip, resulting in a multi-core processor. Each core maintains its architectural state and appears to the operating system to be a separate logical CPU. Symmetric multiprocessing systems that use multi-core processors are faster and consume less power than systems in which each CPU has its own physical chip. Multi-core processors may complicate scheduling issues. Researchers have discovered that when a processor accesses memory, it spends a significant amount of time waiting for the data to become available. This situation, known as memory stall, occurs mainly because modern processors operate much faster than memory. A memory stall can occur because of a cache miss, which refers to accessing data that are not in cache memory. The image at the top left illustrates this memory stall. In this scenario, the processor can spend up to half its time waiting for data to become available in memory. To remedy this situation, many recent hardware designs have implemented multi-thread processing cores in which two or more hardware threads are assigned to each core. That way, if one hardware thread stalls while waiting for memory, the core can switch to another thread. The bottom left image, figure 5-13, illustrates a dual-threaded processing core on which the execution of thread 0 and the execution of thread 1 are interleaved. From an operating system perspective, each hardware thread maintains its architectural state, such as instruction pointer and register set, and appears as a logical CPU that is available to run a software thread. This technique, known as chip multi-threading, is illustrated in the image on the right, figure 5.14. Here the processor contains 4 computing cores, with each core containing 2 hardware threads. From the perspective of the operating system, there are 8 logical CPUs, as you see in the bottom image. Intel processors use the term hyper-threading, also known as simultaneous multithreading, to describe assigning multiple hardware threads to a single core. Contemporary Intel processors, such as the i7, support 2 threads per core, while the Oracle SPARC M7 processor supports 8 threads per core, with 8 cores per processor, providing the operating system with 64 logical central processing units. On symmetric multiprocessing systems, it's important to keep the workload balanced among all processors to fully utilize the benefits of having more than one processor. Otherwise, one or more processors may sit idle while other processors have high workloads, along with ready queues of threads awaiting the CPU. Load balancing attempts to keep the workload evenly distributed across all processors in a symmetric multiprocessing system. It's important to note that load balancing is typically necessary only on systems where each processor has its own private ready queue of eligible threads to execute. On systems with a common run queue, load balancing is unnecessary, because once the processor becomes idle, it immediately extracts a runnable thread from the common ready queue. There are 2 general approaches to load balancing: push migration and pull migration. With push migration, a specific task periodically checks the load on each processor, and if it finds an imbalance, it evenly distributes that load by moving or pushing threads from an overloaded to an idle or less busy processor. Pull migration occurs when an idle processor pulls a waiting task from a busy processor. Push and pull migration do not need to necessarily be mutually exclusive and are, in fact, often implemented in parallel on load balancing systems. Well, I'm sure you all understand this. I'll state it anyway. Mutually exclusive means that when one process is using a data source, queue, or other resource, all other processes are blocked from that resource. The concept of a balanced load may have different meanings. One view of a balanced load may require simply that all queues have approximately the same number of threads. On the other hand, balance may require an equal distribution of thread priorities across all queues. Also, in certain situations, neither of these strategies may be sufficient. They may, in fact, work against the goal of the scheduling algorithm. This section on multiprocessor scheduling is a little bit long, so I think we'll break right here. Take a moment to look over your notes and make sure you've got a firm grasp on the material we've covered thus far. And when you're ready, come on back and we will continue to part 2 in our discussion of multiprocessor scheduling.